Alright, so we continue with yesterday's session on the sequential circuits, and you see now we talk about D-latch, we talk about flip-flop, and we bit of kind of try to understand how each of these blocks work. And I ask you that there could be a question. A basic question would be what's the D-latch and what's the flip-flop and what's the difference between them. And we've seen that the D-latch looks like this in the left, as you can see from the pointer. It is basically when the enable signal or clock signal is issued to this circuit, D goes to Q, and that is what we see that, okay. And we know that how to implement this circuit. We use the just two pass gates right over here and right over here. We establish feedback path. So when the circuit is enabled, clock is issued, D goes to Q, and when the clock is disabled, Q will hold on to previous value of a D. That was it was about. Then I said that okay, we'll use two latches. One use it as a master latch, one use it as a slave latch, and accordingly we explain the operation of this. So the basic difference, as Shweta yesterday told correctly, that's the only difference you need to remember. Latch is level sensitive. That means based on positive or negative, when there is a signal, we instead of calling it clock, we'll call it as an enable signal. When there is a signal, enable signal, and it has a positive level or negative level, logic 1 or logic 0, the circuit will start working. When there is no enable signal, the circuit will stop working. And what is the flip-flop? Flip-flop are the edge sensitive. Again, the positive or negative. Edge means just when the signal, clock signal, makes a transition from 0 to 1 or 1 to 0, circuit will be active. However, in the case of latch, you have to have a level, positive or the negative, then the circuit will react. So that's the only difference. You can just tell them and how we can use this. That's the working principle of this too.
Sir, why D-latch is an level sensitive and flip-flop is an edge sensitive?
Okay, that's another good question. Why it is level sensitive and why it is edge sensitive? I mean, based on the way we have constructed them, accordingly they are operating like this. So here you have two transmission gates, and we have used the clock and clock bar, and here also we have used clock and clock bar. But the way we are positioning them in the circuit, accordingly the circuit is reacting to the positive or negative level or positive or negative edge.
Okay, sir.
So just to summarize, we'll say that latches are used to build the flip-flops, because we know that we take individual latches. Each latch is able to store 1 bit of information, and we just take them to construct the flip-flop. And how to construct the latches? We know that we use logic gates to build latches. How? What are the logic gates? We use the pass transistor gates in the previous slides to make the latch. And how to build logic gates? We use the transistors. So transistors are used to build the logic gates. So transistors are in the compound transistors are wired together in a way that forms the compound function. So you see, from transistor we go to logic gate. From logic gate we build latches, and using latches we are able to build flip-flops. And using flip-flops we are going to build registers. Yesterday we saw that there are puts few latches in series with each others, and each latch will be able to hold 1 bit of information, and we can see that we can create the register. Register is just a place where information in terms of bits are stored. Now we have to pay a little bit attention to this CMOS fabrication and layout. A few idea and little information I have already passed to you in few of the earlier sessions. There I explained you about CMOS inverter. If you remember, I talked about how the wafer looks like. This is the wafer, okay? And have you seen the wafer in real time ever?
Yes, sir.
Yeah. So usually, as a physical design engineer or as a VLSI engineer, this wafer has the dia about 15 to 30 centimeters. That is the diameter. So you call usually in the industry they use these words: 4-inch wafer. They use these words: 8-inch wafer. They use these words: 12-inch wafer. So obviously India is a design house, and we don't have a foundry. Just like, do you know what is a foundry? Foundry is a manufacturing plant where these chips will be fabricated. India will design its own chips with different companies, but the foundries, it will be sent to foundries. Foundries are there. These are the foundries: TSMC. Then you have foundry from Qualcomm. Then you have foundry from Intel. Then you have foundries of Jazz Semiconductor. Then you have foundry Bosch Semiconductor. There are many foundries. This is all there to actually fabricate your circuit. So what they do is that they take this kind of silicon wafer and they process it. We are going to see how these fabrication steps are done, and before that, one more important term, that is layout. So as a physical design engineer, you should be knowing the concepts of layout, but just little bit of information about the CMOS fabrication, as is also there in your syllabus. So I would like to pass on this information to you. So what you see here, transistors are fabricated on thin silicon wafer. Can anybody tell me what could be the thickness of this wafer? It's also called as handle, silicon handle, or simply say wafer. And when we fabricate the devices into it, then we also call it, we use it as a mechanical support, or another word that we have used, we call it as a substrate. Okay, so the thickness is usually 500 micrometer. Okay, so if like I have to draw this silicon wafer, and if you remember from the previous slide, somewhere here we are going to fabricate our transistors, right? Okay, this is NMOS and PMOS. So this is called a substrate. So this is basically a 500 micrometer thick, so small. And you can imagine then the thickness of these regions, how deep they can go. So they are usually about 10 to 20 micrometers based on the technology and all that. So these wafers, they serve as a mechanical support because you are going to fabricate the components inside this wafer, right? So they are very good to act as a handle or act as a support where the components will be fabricated. And also when you make the circuit, let's say we fabricate CMOS inverter circuit in this, then also somewhere we know that I told you that this was a p-type substrate, and then you make here somewhere a contact and we call it P plus. So somebody asked me like why you want, so it's just like to have you want to fabricate this area as a P plus contact, that is called as a for the electrical connection, because I told you that you have to ground it, okay, and some other contact that you will fabricate, you have to connect it to VDD in case of the inverter. It just to make sure that circuit will work properly. So just we are talking about substrate now. So we know that all the transistors right here will be fabricated in this substrate, and they are also excellent mechanical support because you need a base. They are also called a substrate, base, or mechanical support, or simply say wafers. Okay, so what we need
Sir, for a chip, we may need 1 centimeter or 2 centimeter, something like that, that much of area, no, sir. This is almost like half feet to 1 feet. Are we going for manufacturing, or they are going to cut this, or how it will be, sir?
Right, it's a good question. So you see, this is like 15 to 30 centimeters diameter, or let's say 8-inch wafer or 4-inch wafer. Your each individual chip here is about, let's say, 100 micrometer by 100 micrometer, or 100 micron square. So you see, so small area you took to fabricate one microprocessor chip. Suppose that was your task as a designer. So there'll be, let's say, 500 chips in this wafer, or it could be 1000 chips, or it could be even 10,000 chips. So each individual chips is also called as silicon die. Each individual chips, right over here you see this, these are the things. So they are like 100 by 100 micrometer square, and they are called as silicon dies.
So in the end, are they going to cut this, or how it will be, sir?
Right. So once you fabricated your circuits, so they do this wafer cutting. They have some equipment.
And this supposed to be in rectangular square, no sir? It is in circle.
Yeah. Some area will be wastage. Obviously, they will have, just like in, let's say in your, now the Diwali is coming on I'm not sure in Bangalore or in Karnataka or in different states what that dish is called. Is like you make this basin. I hope you understand this Hindi. And what they do is that using some utensils, like they make these slices like this, rectangular or any design, and then they take the individual slices and put in the pan with lot of oil and fry them. We call it as, I don't know, in Marathi they call it as a shankar pade.
Okay. No, so, sir, in manufacturing, they can, manufacture as a rectangular square, no, sir. Simply why they are doing this waste?
Yeah, that area goes waste, but they make sure that only little area goes waste, because you will have a very small areas that they will separate the chips. Some area will also will always go waste, but that's not in, because the area that will go waste, they don't have a design in that area. They will put all the designs in the center of a chip. That is how that is manufactured. Is that answer to your question? Yeah.
Yes, sir.
Yeah. So just to tell you that this is the basics of you just need to remember this information. So what we need is that set of mask. Now what is mask? I'm going to explain that. So you have to define set of mask that will be used to manufacture different parts of this transistor circuit. So what is the transistor circuit? Let's say you are trying to fabricate a CMOS inverter again. And the size of the transistors and the wires by which those transistors will be connected will be set up by the mask dimensions. So for instance, I have explained you earlier, you are going to fabricate the CMOS inverter. So I know that in CMOS inverter, I am going to use two transistors out here. This is input A and this is output Y. And I know that these two, the drain, source, drain and source. So I see that these two drains are connected, I call it as the output. The two gates are connected, I call it as the input, right? And the source of PMOS is tied to VDD and the source of NMOS is tied to ground here. This is ground. This is how I know this connection. So what I'm saying is that transistor size is set. So I'm designing this circuit using 14 nanometer technology. So I have a technology library and all that. And these are the wires. So when I say the polysilicon wires, which is going to connect two gates, the dimension of that polysilicon is already defined in the library, the width, for example. You cannot have a larger width, okay? So as a PD engineer, when you will do that, you should know this information, which is already supplied with the library given to you, okay? And when these dimensions are fixed, so you use those mask or those rectangle layers for polysilicon, for N diffusion layers, for the metals, etc. So those widths and the lengths of those each individual rectangles is already predefined. So if you draw a rectangle like this could be metal or polysilicon wire, and if you violate some dimensions, for example the width here and the width here, then when you run the DRC using the EDA tool, the tool will show you the error. So they will immediately prompt the designer, go back to your design, reduce this width here. So you will have to again adjust your mask, Okay, so these are basically mask layers.
Sir, do we have control to adjust the mask, or that is in standard? No, sir. The tool will take care of it. I believe.
Good, yeah, tool will take care of it.
So, do we have control to change the width of the mask?
Yeah, I mean, when you want to, let's say, connect these two transistors by the polysilicon gate, so you will choose the polysilicon layer from the library. In the library, you will have such box in the right hand side, and they will show you the layers, different layers. They will say this is layer poly, this is N plus, this is P plus, this is contact in the tool. Then you click your mouse through the mouse on the poly. You select the poly, and this is your schematic drawing area or layout screen. Then what you are doing is that you have picked up two transistors here first, and then you are connecting the gates of these two transistors through this polysilicon. Okay, you call it as a poly. So you can these cells and these transistor cells are already defined, but this rectangular you need to draw sometimes. This rectangle you will draw. So this width you will choose and you can adjust. As long as you don't violate the design rules already set and predefined, you can adjust. This is in your control. They will always give the minimum dimension.
Okay, sir.
Okay? Because this minimum dimension is another word, it's called as resolution. Because when you will your design file will go to the foundry for the manufacturing, this minimum dimension, or in other words they call it as a resolution, is limited by the manufacturing process. So manufacturing process is 14 nanometer, you are designing it. So everything is set, all rules are set by the foundry. Foundry cannot give you a minimum dimension. If suppose they give you like 10 nanometer is the width minimum, and if you try to draw 8 nanometer, you will have the DRC error, because the foundry will not allow you to do the 8 nanometer wire. Okay, so what to do? For instance, I want to fabricate a particular circuit. So what I want to do is that I want to understand, although I am a RTL engineer or I am a physical design engineer, but if I have a knowledge of about how chips are getting fabricated in the foundry, that is helpful. Okay, so what you do is that there is one term called as photolithography. Photolithography. So what I do is that photolithography is just like a printing technique. Just like you have a wedding card, you go to shop, or you have any birthday card you want to print, you go to shop and tell the vendor that I want to have this. So he asks you for the matter, where you have a design matter, okay, this information and all these things. He will use different inks at different area of the wedding card. Here you will have an address with the red ink, here you will have names with the blue ink, and so on. So usually you know that by the screen printing technique, he has machines, how he prints all. He cover one area while depositing a particular matter with specific ink color. Then he cover this area after printing, and he deposit a matter with another color on this area. So that's why when he cover a particular area, that he covers using the mask. So it's just like a same technique is used to fabricate your integrated circuits. How? So this is our substrate right over here. So this is our substrate. So on the substrate, what we do is that we perform a series of different steps. So for instance, layers, different layers of the chips. It means I want to fabricate CMOS inverter. So I need to know where will be my N plus diffusion region, where will be my N well, where would be P plus diffusion regions, which areas of the diffusion, sources and drain, we know that gates of the two transistors are connected through polysilicon. So I need to know which area on the substrate I will draw the polysilicon to connect them. So layers of the chips will be defined through this process that is called as photolithography. So photolithography is just as the name says, photo is there is a use of light. So this arrows that you see, it is called as ultraviolet light. So there is a machinery by which this light is actually enabled, and that light passes through, I'm going to explain this in a moment how this diagram is working. So photo, there is a use of light, and lithography is the process of writing the information. So in this case we are writing the information, means we are fabricating a circuit. So before I explain you these steps, what I want to make one comment: smaller transistors are faster and they consume less energy. So can anybody tell me what is meant by smaller transistors are faster?
Because the channel length is small.
Good. So let's say I have this transistor. Just to revise your concept, this is your source, this is your drain, this is your gate, and by means of some control I am enabling this, and this technology is 14 nanometer. And I have another transistor, the same transistor, but this time this is gate, this is source, and this is drain, and this technology is, let's say, 140 nanometer. So which transistor is faster? Obviously this. Why? Because with the help of this gate control, the charge carriers, whether it's electrons or holes, in case of, depending on what is that transistor, NMOS or PMOS, so these charge carriers will take lesser time to travel from source to drain as compared to the charge carriers that will travel from source to drain in the higher technology. So small transistors are faster, and that's why we say that nowadays the computers are so faster. All the computers and logic chips, they are faster. Why? What does that mean? They are operating at the clock frequency of gigahertz because of this technology scaling. We have seen that, and they consume less energy. What is that meaning? What does that mean? Power. Good. So power, it means I am taking only a small portion of charge carriers, small number of charge carriers. So for instance, I want electrons here, so I am depositing positive charges here on the gates, because usually what is it? MOS. This is metal or polysilicon. We know that nowadays people use polysilicon for a gate terminal, but we are still calling it the MOS. This terminology keeps on continuing. This is SiO2, simply a glass or oxide. So this is insulator, this is conductor, and middle layer is insulator, okay, and this is semiconductor. That's why we call it the metal oxide semiconductor, MOS. So what I am saying is that I am depositing positive charges here on top of the gate, and I am having the opposite charge carrier. So what I am having, this creation of electric field. I am establishing electric field. So what I am saying is that smaller transistor will need less energy because they are so power efficient. They just need little energy for their operation. So it means I am needing only few number of charge carriers here to charge the gate and to make the transistor work, as compared to this technology. I will need large number of charge carriers. It means I will need larger electric field. Obviously it has related with the energy. Okay. So now coming back to your explaining these steps. So what I will do is that I start with the substrate, then I will use the photoresist. What is photoresist? It's just like a plastic, but in the scientific world we call it as an organic polymer. Organic polymer. Again I am asking you, I have asked you already, take the notes when I am explaining you. That is much efficient way of learning through the material, and you can understand what different things you are doing here. Okay, so keep taking. So this is called organic polymer, a special kind of material where I deposit it on the photoresist, and then I expose this, and then I put the mask here, mask here, mask here, and mask here. Mask means it's just like we are covering our face in the coronavirus crisis through the mask. So it means we are not exposing our particular area on our face to the outside environment. So similarly, masking here means I am not interested to expose this particular area to the ultraviolet light that is coming over. So when I put the mask, I properly position the mask in this area, and then I expose this system to the light coming here. So the light is coming and going straight down over here, but the mask is preventing the light rays, ultraviolet rays, to reaching to some portion right here and right here. So what is happening is that this particular area gets melted. I call it as that is getting softened. So it's just like that gets melted or that gets softened, so that I can later remove it. So what I'm doing is that photolithography. So this area then is taken off, and finally depends on the photoresist type. I have a positive photoresist and I have a negative photoresist. It depends what kind of photoresist I am using. I will also answer why in a moment. So there are two types of photoresist. One is called positive photoresist and one is called negative photoresist. So just take a look at these two pictures and tell me after this step what happens in the final output. Anyone? So if I use the positive photoresist, so when the light went here, right over here you see light went here, so it means this area got melted, this photoresist got melted, this portion and this portion of the photoresist I protected through the mask. So it depends on, because why I did this, because I want to etch this area and this area into the substrate. Maybe I have a need to deposit here dopants, so that's why I expose this area. Another area I covered through the photoresist, and after the etching process I will take this photoresist also, I will strip it off. Okay, in case of negative photoresist, what I am doing is that negative photoresist has a property where the light went, just like here and here, that area remained intact, other area of the photoresist got softened and that got melted. So it depends on what kind of you want. So what I want to do with this, maybe I have a need to have a dopants area, maybe I want to fabricate envel here, that's why I did this and I use this special negative photoresist. Maybe here I want to do something else, maybe here I want to do something else, and that's why depending on your requirement we use different kinds of photoresist. Is that clear to you? Okay, can anybody tell me in industry when the chips go for fabrication, what photoresist people you prefer in fabrication, positive or negative?
Positive.
Why?
That is easy to decide the area.
Okay, so that's just a basic and a simple question. It's not that important to know, but depends. Sometimes they also use for special needs, they can use negative or positive, but mostly you can just Google and find which register they use and all that, but both have their advantages and all these things. So I just gave you a brief idea about how the area is selected through the what is the meaning of mask, what is photolithography, and what is photoresist. Photoresist is just a plastic or say a very thin layer that people use to process the substrate. So for instance, now let's say I want to build an inverter circuit. I hope you remember these slides before. So how many masks I need? Inverter circuit. So again I take you to schematic to understand you better. Inverter, I am very familiar with the inverter circuit now, right? I have input, I have output. This is VDD, this is ground, that is drain of a NMOS, source of NMOS, that is source of a PMOS, and drain of NMOS. I know that the two polysilicons are connected, the two gates are connected. What are the two gates? Here. Then drain and drain of these two transistors are connected. So inputs and outputs are defined here. Now source is tied to VDD. Here source is tied to ground. And the body of PMOS I show with schematic. If I want to show it through schematic diagram, I would say the body of PMOS, which is N-well, I show it this way. It is tied to VDD. Or I would say it is tied to source, and ultimately source is tied to VDD. Here the body of NMOS is tied to ground, or it is tied to source, and source is ultimately tied to ground. So this is how I represent. Look at this. This is called as a top view. Top view in the sense, if I have this silicon wafer here, and then I have a small area of a chip area in which there will be 100 such areas because there are 100 chips. So same pattern I am going to draw. So in this area I am going to have this CMOS inverter chip layout. So what I am going to do is that I need mask. Mask is the area in which I will see which component goes where. It means I want to choose where N-well goes in the silicon wafer. For example, this is the cross section. When I will say, you need to understand this very well actually, okay? Don't miss this. So this is your p-type substrate, and here somewhere we have N-well, and then here you have these two transistors. This is N plus. So we have seen that. Okay, I show you here. Look here. So I have this p-type substrate. I have NMOS here. I have PMOS here, and I have well-made connections with the mask. And so this is called as side view or cross section.
Sir, mask is an insulator or a connection like an wire?
What is the question?
Mask means, is it acting as an insulator or is it act as an wire?
It's acting as an insulator. It's just like to protect, to define that area. Sometimes it is also used to protect that area where we want our component to be fabricated. For instance, you see now this top view. What you see here, first of all, how many layers we need? We need N-well, we need polysilicon, we need N diffusion, we need P diffusion, we need contacts, and we need metal. Why we need contacts? Contact is just to connect metal to different layers, because we know that through metal only we will have access to those points. So what mask does? Mask will specify where on the chip these components will be manufactured. What are those components?
Polysilicon is a mask here.
Yeah. This is mask. So this is mask for N-well. This is the mask for polysilicon. These are the mask 1 and 2 for N diffusion. These are the mask for P diffusion, and then there are contacts here. And this is final mask. So total we have 6 masks. So when you sometimes you will as an engineer in the industry, you will also hear this word 3 mask process, 6 mask process, or N mask process. So N could be any number. So at that time you need to, as a fabrication engineer, of course as a PD engineer or VLSI engineer, you don't need to know this much detail, because I just told you in India we only design the chips. We don't have foundry, so we don't fabricate, right? So that's how the meaning of it. Just a moment, I am going to switch on my fan here. All right. So can anybody take a look at this picture, the top view, and try to see where are the areas where I am defining the mask? This is the chip area, for instance. This is my chip area. This area is about, let's say, 10 by 10 micrometer square. and I have a particular technology. So what I'll do is that, look here, I will just for your explanation I will just erase all the ink, and now to help you better I will use the laser pointer. So here, this is anvil. I want anvil to be made here. So look, this one, this square here. Then in anvil, I want, which transistor goes in anvil?
PMOS.
Correct. I am using the P-type substrate. Come back to cross section. When you are confused with this top view, just try to have a look at cross section. Cross section is just nothing but the side view, right? It's just like you, for instance, you have two breads and you put in between the two breads you have lot of vegetables, and then you got your sandwich done. You put that sandwich in a nice plate, and then you take a knife in your hand and hold your plate on which your sandwich is there, and then cut the sandwich from the top in the middle, and then you have two slices of sandwiches. One you give it to your friend and one you keep it yourself, and now hold that sandwich like this and see all the layers that you can see. So what is that view?
The left side one.
Did you understand what I just explained you?
Yes, sir.
Let's say you have two breads. Then in between you put mayonnaise, you take several vegetables, you have a lot of different ingredients, and then you take one bread on top of each other, and then you cut that sandwich from the middle. So then you take one of the slice portion and you are ready to eat. But I want you to see the different layers. The top layer is the first bread. In between you have a layer of vegetables and different sauces, and then final is again your bread. So that view is what view is that? Are you getting me or not?
The left side one.
Yeah, this one. This is the cross section, right?
Yeah.
And if you look at this from the top, then it is called as a top view. If you look at from this top, this component, then it is called as top view, which is shown over here. So look at this view and this view for a moment. I let you 2 minutes to observe that. Can you see some connections there? So see, here you have a P substrate, okay? So I know that I look at the top view and I know that from looking at the top, the substrate is beneath. I know that. Then I take a look at NMOS transistor here. Where is my NMOS transistor? Okay, I have a dopants here, N plus, N plus. I go here. Do you see N plus and N plus? And where is the mask for these dopants? Here, N diffusion. Yes or no? Look, here is the N diffusion. So here is the mask. Then I go to anvil. Where is the anvil? Here is the area I want anvil to be constructed. Where is the mask for anvil? Here I put the mask. Then I have inside anvil I have P plus dopants, heavily doped, P plus and P plus. I go to top view again. Where are the P plus? Here, this square. This square. Where is the mask for that? Right over here. Look. So this is how you can observe each of the mask. And finally, metal. What is that metal? These slash lines. That is all metal. So here is the mask for that. Here is the mask. In this area I have metal. On the top view I see that this is the mask. You see, this is the mask I have, and this is covering this area right here. Then again I have a metal in between here. So if I come down right over here, look, this is the mask. I have it. So I hope you are following me, right? So we need 6 masks to fabricate such transistor, and this mask will tell us where each of these things we need to be fabricated. So this is a cross section, this is your top view. Now how we will fabricate that? Because as a PD engineer You have used the technology file and you now have a good understanding about what is mask. These 6 are the mask. They are indicated by different colors and layers. And we also now have studied how to understand the cross-sectional view or side view and what is the top view. So we know that. But now you define the mask, and this is nothing but your layout. So this is called as your layout. Did you get it?
Yes, sir.
So in the library, when you actually, most of the times, if for instance you are an analog designer and you are designing an amplifier circuit, right? So what you will ready-made way have, it will be ready-made there. The cell, the layout for the PMOS transistor and the NMOS transistor. So you will directly pick up these two masks from the library, and only thing you need to use is that make the input-output connection. For instance, you will draw the poly, you will have the output Y. This, you see, the source and drains are connected, so this is the output of CMOS inverter. And then you will draw the metal here to establish the ground connection. You will draw the metal here to establish the VDD connection. That's it. Even the body will be tight of the NMOS. The body of the NMOS will be shorted ready-made, and the body of PMOS will be shorted ready-made, and only you need to draw metal and the poly. So nowadays there are many facilities in the advanced computer softwares that helps the designer to shorten the turnaround time, the chip design time. So let's start with the, for instance, this is the task for you. I only want to fabricate NVEL. I don't want to fabricate CMOS, but just I give you a task to fabricate NVEL. How will I do? I am given the P substrate. You see now, this is about 500 micrometer thick. So I call it a substrate or handle or simple silicon wafer. And I am given a task or to fabricate an NVEL into the bare P-type silicon wafer. So what I do is that first step. So NVEL means I know that in the P substrate, I am asked to fabricate NVEL. Finally, it will look like this. This is NVEL. So NVEL is nothing but dopants. So I want to convert P-type material into N-type of material. And where? For the entire substrate, only this portion. Only this portion I want from P to N-type. So I will use dopants. What kind of dopants those are?
Pentavalent.
Correct. We use the arsenic or boron. We'll use arsenic to make the P-type to N-type, right? So we'll have a process. We'll perform that step and that. So now what I first do is that I will just protect this P substrate, because I want only in this portion. In particular, not the whole wafer I want NVEL. I want only a size, a small portion to be NVEL. So I will just grow one protective layer of SiO2. It's just an insulator on top of entire P substrate. So this is figure number B. And later I am going to remove it also. We'll see that. So how I grow this layer here in the figure? I will take this wafer, and there is a machine in the clean room that's called furnace. It's a high temperature furnace operating typically at 900 to 1200 degrees Celsius. And that process I will perform, the machine will perform, that will cause this silicon to interact with the oxygen. There will be a gas in the furnace at very high temperature, and there will be a interaction between silicon and the oxygen, and then very thin layer, about let's say 100 micrometer, throughout the entire surface substrate will be grown. So I call it as a SiO2 layer. Then once this process is done, I will go to step number 3 or figure C. then I need to pattern the oxide to define the anvil. Why? I'm doing the patterning here because I want only in this area anvil to be fabricated, not here some other area. So what I'll do is that this organic photoresist, it could be positive or negative, but just think now it as an organic photoresist. I will expose this photoresist, and in this particular area that photoresist gets softened or it will be melt away. So this area will be open. After the ultraviolet light will come over all the surface, and only this portion of photoresist got softened. Why? Because I let the light to fully come over here. Other area I have defined the mask. I had put up the mask here. Okay, so only light went all the way and it softened the photoresist in this area, and then I stripped it off. Then number 4 step. So like I said, the photoresist is exposed to the anvil mask. Okay, I had the anvil mask here, and then I came to this step, and then I removed this photoresist from this area, and now I am at the step D. Now what I do, I want to etch away this oxide in this area also. So what I will use some acid. It's called hydrofluoric acid. So hydrofluoric acid, I will put, let's say I have this pot and there is acid over here. This is called HF. So I will dip this entire wafer in this acid, this way or this way, this wafer. So only in the area right over here where the oxide is not protected by the photoresist will get etched away, and this photoresist in other area will protect the oxide. I don't want that to be also etched away. I only want the oxide here to be etched away. So we are at step E. Now I will, after this process, I come to this. So what I just do it, I take off the photoresist away. I just stripped it off. And finally, what I do is now, I am at this step. I will use 2 special processes now to insert the atoms. I want dopants now. I am done now. So what I'll use that well will be formed in this area, as I said now. So because in this area is not covered by the oxide now. Other area is covered by the oxide. So what I'll do is that I will use the diffusion process. Another step using some machine where I will insert the dopant. Okay, I will put the wafer in the furnace. It will have a gas at some temperature, and that gas will have a dopant. Those dopants will go inside and it will start penetrating the wafer until it forms the area. Okay, this little bit of so now this way I am able to form my anvil. Do you see the anvil is little bit in this area also and in this area? Ideally, what should I want? The anvil, because oxide is covering this point also, right? So ideally I should have the anvil like this. But why is this extra portion? This is called as lateral diffusion. Yeah, it just penetrates. This is the fabrication error, right? We can't do that much with that, right? So when you have this process, the dopant atoms go inside the substrate and it starts penetrating until a certain depth. How to control this thickness? You can go till the whole substrate also, but I want to stop here only. That is set by the temperature and the thickness control machine. Okay, and final step, you will have your anvil in the field substrate. Now what are the remaining steps that we want to do? Did you understand how to fabricate a simple anvil in this CMOS fabrication process? Now what other areas we want to fabricate? You see, we want to fabricate so many other things. What are those other things? We want to fabricate, we just fabricated anvil. Now the next step would be polysilicon, N plus diffusion, P plus diffusion, then put some contact and the metal. And that's why this layout is helping us. The layout helps the fabrication engineer to define the areas in which the processes will be done. So do you have any question based on these steps that we explained so far? Any question there? Okay, so can anybody tell me that they have some problem in understanding this side view and this top view? Or I assume that you have a good understanding about that. If not, then I am giving you an assignment now. You want to show me, okay, very simple. Y equals A dot B. This, what is this logic function?
NAND gate.
Okay, so this is NAND logic. And how do we implement it? Using the transistor, using the logic gates. We see that this is 2 input NAND gate, so no, that became OR actually. So it would be like this. For instance, you have A and you have B and you have Y. Or even that, I want to give you a simple example. Tell me what is this?
Fast transistor.
Right. This is G and this is, let's say, G1, this is G2. Okay, so now I want you to draw the layout for this one using this 2 diagram. I gave you how I draw it for the inverter. So please show me the top view and the cross section view of this particular logic. And you have all these layers with you, envel, polysilicon, diffusion and all this. Is it simple to draw?
How we can connect it to some transistors, sir? That is, we are not sure.
How you are not sure how you will connect that?
Two transistors.
So I just told you, you see now this is like source and drain. This is also source.
Yeah,
and
through
drain.
metal contact.
Yeah, just connect these through the metals. So you have these metals, and then gates are individual. Very simple.
Okay.
And you can
To
show
connect from one transistor to another transistor. So what we should use, metal or wire?
Say again.
So we need to connect to two transistors, right?
This pass gate, you want to show me the cross section and the layout of it. So cross section and top view you want to show me. Yeah.
Okay, sir. So there we need to,
Yeah, your voice is getting cut. Yeah. Hello?
Oh, able to hear me, sir?
Now I can hear you.
Okay, sir. To connect two transistors in between, what we should use? Metal in between, or wire, or what we should use?
Yeah, good question. So here how we connected these two transistor inverter? See, the gates of these two transistors are connected through what? Polysilicon.
Polysilicon. Okay, okay.
And,
okay, sir. So
yeah.
one transistor to another, we can use polysilicon.
Right. Okay.
Okay.
So you just come up with this, in this way you can create a layout for, we are going to see this also, we are going to create the layout also for different logics. Okay, so I just gave you a hint about how the things will look like, and always when you will create the layout, two things you would visualize: cross section and the top view. Okay, so we would like to stop here for today's session, and we continue as we go ahead. Is there any questions that you have? Let me know.
Sir, I have a doubt regarding last class.
Yeah.
Regarding that pass transistors. Can we construct a circuit using PMOS, only with PMOS and only with NMOS? Is it possible?
Pass transistor only with what?
Only with NMOS or only with PMOS?
Yeah, like I said, if you want to pass only, let's say, logic 0, so we understood that, okay, NMOS are good for that.
Okay.
If we want
in that case, we are only using NMOS.
Yeah, only, let's say we want to pass strong 0, then use NMOS.
Okay, then, suppose we are constructing an AND gate.
AND gate.
Using pass transistors.
Yeah.
Can we use this NMOS only?
Why would you do that? But don't you see the signal will be degraded, because we have seen that when we combine NMOS and PMOS in parallel, that acts as a good transmission gate to pass both the logics without degradation.
Okay.
Right? So we use the transmission gate just to pass a good logics at the output.
Sir, we cannot construct an pass transistor only with NMOS, no sir. That is not possible.
It's possible. See, what is pass transistor? It is passing some logic. Again, so let me make three
It is
sentences.
passing whatever the input is there, same in the output without degrading, either 0 or 1.
Correct. NMOS is good for passing a good 0. PMOS is for good 1, but not the opposite.
Yes, then we need both the transistor. Alone PMOS it is not possible, no sir.
Yeah, that's what I said, right?
Okay, sir.
Yeah. So, okay, so come up next time with, let's say you want to draw the layout for the AND gate, NAND, Y equals A and B whole bar, and other logic is the transmission gate. So just try that, is for information.